We are looking at a massive drop of new scientific data today, and it paints a crystal clear picture. The planet's operating system is updating at breakneck speed, and India is sitting right on the front lines. Take the latest coastal projections. Under current emission trends, what used to be rare once-in-a-century floods in Southeast Asia are now projected to happen every single year. For major coastal hubs like Mumbai or Chennai, this is a direct, flashing red flag. And it's not confined to the coasts. Paleoclimate records looking back 2,000 years confirm that droughts in mainland Southeast Asia are tightly linked to extreme precipitation in Central Asia. As that large-scale pattern intensifies, it directly scrambles our own already unpredictable monsoon cycles. This animated diagram shows how low cloud cover over tropical oceans acted like a thermal shield, muting global warming for 47 years. Models indicate as these stratocumulus clouds dissipate, masked warming will hit us as a sudden, sharp spike in surface heat. Between this accelerating sea level rise and hidden heat spikes, our current coastal and urban infrastructure is operating on completely obsolete historical data. Water stress is becoming a universal modern experience. A recent survey out of Utah shows massive anxiety over the rapidly drying Great Salt Lake. Look at the people walking across this cracked lake bed. It is the exact same existential dread we saw during the recent Bengaluru water crisis. But people are actively hacking the system. In Bihar, community participants have successfully crowdsourced accurate contamination data by collecting local groundwater samples themselves. They are generating the exact environmental datasets that professional scientists need to map the crisis. That kind of local vigilance is desperately needed elsewhere. Right now, river sand and gravel are being extracted way faster than nature can supply sediment, causing severe bank instability and water quality deterioration. That is a structural threat, directly undermining Indian construction and infrastructure. We do have proof that localized action works. Over in Brazil, the burned area in the Amazon just fell to its lowest point since 1985. Part of the solution is indigenous, community-led programs that proved incredibly effective at protecting rainforests, even through the pandemic's severe economic shocks. We need to scale those solutions fast, because historical extremes are volatile. Fossilized pollen shows that ancient global warming triggered millennia of continuous megafires across Europe during the Triassic period. Today, experts warn that concurrent climate patterns are pushing Somalia toward extreme 1997-scale superfloods. To get ahead of that volatility, researchers are deploying low-cost, underground sensors. By measuring soil and root moisture below the surface, they receive a much more accurate, hyper-local indicator of wildfire risk than they ever could from traditional above-ground weather data. Whether facing droughts or floods, deploying localized tech and relying on community crowdsourcing is the only realistic way we can adapt to these extremes. Nature is already adapting in bizarre ways. In the arid Australian outback, decades-old toxic mine waste is crawling with microbes that are actively transforming supposedly immobile heavy metals into mobile polymetallic nanoparticles. It is a biological breakdown highly similar to the extreme microenvironments forming inside massive Indian landfills like Gazipur. Biologists discovered a tapeworm parasite that completely hijacks worker ants. It alters their metabolism to act like queens and actually extends their lifespans. Nature is mutating to survive its own toxic environment. In the deep tech sprint, an AI agent just successfully ran complex synchrotron X-ray measurements completely autonomously. Meanwhile, scientists created a frozen liquid core optical fiber that couples light and hypersonic sound 1,000 times more strongly than standard glass, massively dropping the energy demand for signal processing. We also have a new 2-layer spin transistor made of a single crystal. It integrates magnetic and semiconducting functions perfectly, eliminating interface losses and switching with zero space charge limits. Add to that 2 color lasers that can steer electron currents through semiconductors without applying an electric field, and glass-coated aligned graphite microcrystals, achieving stable diamagnetic levitation above permanent magnets. These abstract physics breakthroughs are the literal blueprints for making our next generation of smartphones, computers, and electronics significantly faster, colder, and hyper-efficient. On the human biology front, A massive study analyzing nearly 49,000 brain scans has successfully mapped distinct aging signatures. They can trace the brain's physical links to dementia, addiction, and mental illness long before severe symptoms hit. Similarly, researchers have pinned down specific genetic variations linked directly to sudden cardiac death. With the alarming rise of sudden, unexplained heart attacks among young, seemingly healthy Indians, having the data to screen for these genetic markers provides a crucial preventative tool. And in neuroscience, we've learned that brief ripples of activity in the hippocampus actually prepare the brain for surprising events. Those brainwaves, once dismissed as background noise, are actively building a predictive biological model of our reality. Medical science is rapidly moving beyond treating illnesses after the damage is done. We are now actively mapping and predicting our biological futures in high definition. We are also mapping the future from orbit. The US-India NISAR satellite, a joint NASA and ISRO mission, is officially delivering data. Using advanced radar, it can penetrate surfaces, revealing the hidden subsurface structures and crevasse properties of Antarctic ice from space. NASA is also launching new suborbital Earth venture missions to track precipitation-driven landslide dynamics, while tiny, low-cost CubeSats are taking high-fidelity, time-resolved measurements of Earth's radiation belts. Further out, scientists are gearing up for a major impact. An abandoned SpaceX Falcon 9 rocket is on track to crash into the moon. Astronomers are eagerly waiting for it to hit. The resulting multi-kilometer dust plume will test our methods for pinpointing lunar impacts and help plan future seismic experiments. Tracking that space debris and unearthing hidden global data is essential for securing our future, both off-world and back here at home. Let's sprint through deep space. Astronomers caught a recurring supermassive black hole eruption in real time, flashing near its absolute luminosity limit. Elsewhere, a massive black hole jet is stirring up a neighboring early universe red potato galaxy so violently that the turbulence is physically suppressing new star formation. In the Jellyfish Nebula, multi-wavelength data confirmed that 2 supernova remnants were born from a binary pair of stars exploding thousands of years apart. And the James Webb Telescope's mysterious little red dots are now believed to be the dense, supermassive ancestors of today's globular clusters. This animated diagram visualizes a wild new theory about our own neighborhood. Simulations suggest the disk of the Milky Way galaxy flipped its orientation in the deep past, thanks to an ancient cosmic collision that radically altered the orbits of early stars. Finally, fast radio bursts have helped map the universe's missing ordinary matter, tracking it to massive, low-density halos of gas ejected millions of light-years outward. And closer to home, new data hints that solar energetic particles actually triggered anomalous atmospheric heating during a global dust storm on Mars. Observing this extreme, violent volatility in deep space is exactly how astrophysicists are finally grasping the ultimate life cycles and mechanical rules of our own galaxy. For all our high-tech sensors, some tasks still require a human pulse. In Sweden, researchers are relying on human volunteers instead of AI to classify images of the Arctic sky. It turns out, AI algorithms consistently fail to tell the difference between thin clouds and the aurora borealis. And that human eye is critical, because perfectly clear conditions are required to measure upper atmosphere winds and prevent severe disruptions to satellite communications. From college kids in Bihar crowdsourcing water data, to ISRO mapping the globe with radar, to everyday people beating out AI at reading the night sky, we are actively navigating and surviving the ultimate sci-fi timeline.